So if we're far away from our charged surface here, we want to find the electric field at some point P right here. Or we'll say that we want to find the electric field on the edge of my surface, all right? Well, over here, for my whole cylinder, I've got two surfaces. And we know that for a charged conducting sheet, the electric field is always going to be perpendicular to the surface. We saw that last time, okay? So there's not going to be any parallel components, okay? So if I say that this way is X, so here's X, then my electric field is always going to be pointing away from the surface. And we've got two surfaces here. We've got a surface over on this side, and we've got a surface over on this side. We don't worry about the sides of the cylinder because the electric field is parallel to the round part of the cylinder. So we are only going to have two surfaces. Okay, so for our closed surface then, so we're going to write E dot dA, okay? We've got one surface over here, and we've got another surface over here. So we're going to have to do this for both edges of our cylinder. We're going to have E dot dA for both the front and the back of the cylinder. And that's really important, and we're going to do a problem later where we have a bunch of electric flux going in different directions, and we just need to find the amount of flux that's piercing one surface. If we have a cylinder here, it's going to pierce the front and the back, and that's it. On the sides, we don't have any other charge. Okay, so this will equal QA, or Q over epsilon naught, because we always know that this is true, Q over epsilon naught. Since we have a surface charge, we can replace Q if I go down here. So Q will equal my surface charge density times the area. And that comes from the fact that the surface charge density is equal to the total charge divided by my area. So now we can substitute this in up here. And remember that when you're doing this integral, the electric field is constant as we move across the surface. So as we say we moved anywhere on the end of our cylinder here, the electric field is going to be constant. So when our integrals up here, the electric field can come out. It's just going to be a constant value. And our area here, oh, there's some people in the waiting room. I apologize. Okay. So our area that we're going to have to worry about is only the edges of the box here. That doesn't change. And since we picked a circle or a cylinder, the area part is just going to be equal to the area of the circle. But we're going to keep it just as A right now. Okay, so basically what this means is my integral, this integral will become E, my electric field, times A. And I'm just going to call it A. It doesn't really matter what it is right now. And this integral is also going to be the same over here. It's going to be equal to E times A. And this whole thing will equal, I'm going to substitute in for Q now, and I will have my surface charge, right, times the area divided by epsilon naught. So over here, these are going to add together. That's going to give me a 2EA, and my the areas are all going to cancel. So I'm going to cancel the areas, and I'll get a 2 over here. So this will become 2 times E times sigma over epsilon naught. So now my electric field will equal sigma divided by 2 times epsilon naught, right? That's because I had my two surfaces here, and this is my electric field at some point right there, right? So at the edge of my Gaussian surface. All right, now we want to do something a little bit different because let's assume now that we have another plate over here, okay? We have this here, and we want to bring into contact with it another plate over here. So let me. So I have two metal plates now, okay? And if I hook these up to a battery, so I'm going to hook this side up to the positive terminal, and I'm going to hook this side up to the negative terminal. Then here, I am going to get positive charge on this terminal, and I'm going to get negative charges on this terminal, okay? And if I bring my plates close together, this forms a very special device called a capacitor. And when I start adding charge, all of the positive charge on this one will be attracted to this side, and I will get an electric field set up between these two sides that looks something like this. So here's my electric field, and in between the two plates of a capacitor, the electric field is very uniform. So it's all parallel here in between the plates of my capacitor. Okay, so now we want to think about, well, how could we calculate the electric field here in the middle, right? Well, if we say applied the same amount of positive charge to this plate, all of the charge is going to come to this side. So in a capacitor, what we find experimentally is that all of the charge resides inside of the capacitor. And outside of the capacitor, really E equals 0, okay? So here in the middle, we have a very big electric field, okay? And outside, the electric field is equal to 0, okay? So on the outside of this, we really don't have any electric field, okay? So that means that we're going to have to come up with a different Gaussian surface. And so in the case of a capacitor, let's just look at one side. We're going to say we'll make our Gaussian surface look something like this. So one side over here is going to be inside of the plate of our conductor, and the other side will be between this between the capacitor plates. Okay, so now we're only going to have to worry about this surface over here. Okay, and now most of our charge density, all of our charges all of the charges have moved to this plate. So we don't have anything over on this side, okay? So if we have the same amount of charge on this total plate over here, now that charge is doubled because all of the charge has moved from this side of the conductor over to here, and it's being attracted by this side. So we don't have any charge over here. So we're only going to do half of this now, okay? So now we're going to say, well, E, we'll do our surface integral again. So we'll say E dot dA is equal to Q times epsilon naught. All right. So, but now all of my charge has moved to this surface, and I don't have any other charge on the other surface. Okay. So now what I'll find is I am going to get, so I'll still have A times E on, on this side of the integral. And that's going to equal a different charge density. Okay, so now if I take, let's call this sigma 1 from before. So now I will have twice that amount of charge. So my Q, my new charge, Q, well, it's still the same amount of charge, but the area has gotten smaller. So I'm going to have a new surface charge density. I'll call it sigma. Then that's going to be times A. Okay, so I'll call this sigma 1, and this one will be sigma over here. Okay, so now this will equal sigma times A, and I will get the electric field is going to equal, my A's will cancel, and I will get E, and I should have an epsilon naught under here, which is equal to sigma times epsilon naught. So my electric field is going to be higher in between the plates of the capacitor because I have charge on each plate here. Okay, so I'm going to have a different charge density, surface charge density, because all of the charge is on this inner plate here. So if I just look at this one, the electric field will be higher because I have more charge on this plate. Okay, so does anyone have any questions about how we get the formula for the capacitor? If not, then let's look at some homework problems. Okay, does anybody have any questions or any questions about anything we did in class today?
I have a question. It's going to
Yeah.
sound kind of weird, so my apologies. When you see like surface charge density, is it kind of like the charge being concentrated in like one area in a sense, or
Yeah.
not?
Because in a capacitor, all of our charge has moved to this inner surface. And so now our charge density is higher, okay? Because we have twice the amount of charge as we did on this surface. So over here, our electric field is going to be higher. So the more concentrated your charges are on a surface, the higher the charge density is, okay? So if I had, let's say I had, so it's the concentration of your charges on the surface. So yes, it is related to the concentration of your charges. Because
Okay, thank you so much. Thank you.
up here, all of my charge was spread out over the whole thing, but down here now all that charge has moved to the inner surface. All right, so let's look at a problem. Let me bring up the homework. And if you'd like, get out your Wiley homework, and we're gonna look at let's look at a homework problem. And let me share my screen with you. Let's take a look at problem 11 from chapter 23. Okay, so in our problem here, we have this funky electric field, right? And we need to talk about how this electric field changes as we move in X, Y, and Z, because that's going to be really critical to understand this problem, okay? So we see here that our electric field changes with Y. There's a Y dependence, but for the X direction and the Z direction, it does not change with position. So that's going to be important. But let's read the problem. So the figure shows the closed Gaussian surface in the shape of a cube of length 2.2 meters. So each side is 2.2 meters. Okay, with one corner at x1 equals 5.2. So we can see here's our x direction. All right, so this is our x direction right there, and over here is our y direction. Okay, so The cube lies in a region where the electric field vector is given by E equals minus 2.8 times I. Now this I is the unit vector pointing in the x direction. And so what this equation tells us is that no matter where we are in x, okay, the magnitude of the electric field, oh, and I should have drawn it backwards. So no matter where we are on the x-axis, right, our electric field is always negative 2.8. It doesn't matter how our x position changes. So over here, it's negative 2.8. Way back over here, it's always negative 2.8. Okay. Now that's really important because that means that the flux coming into our box, so coming through the surface, I know, I drew all the arrows backwards. I drew negative 2.8 and then I drew the arrow the wrong way. It's pointing in the negative x direction. That's important, okay? So if we look at our cube here, the side that's perpendicular is this front face here, okay? So we have electric field going into this surface of the cube over here. Okay, it's penetrating that surface, but the same amount comes out the other side. So that means that our net flux in the x direction is always equal to flux in minus flux out. Okay? So that's what this is saying. Our net flux in the x direction, it's the same on both sides. It doesn't change. Okay? So flux going in equals the flux going out because our equation for in the x direction does not depend on x. That's really important because we don't need to worry about the x direction. Okay, so let's erase everything. That was for the x direction. Let's take a look at z. So the z term in our equation for the electric field is right here. So it's k hat. K hat is in the z direction, and it doesn't depend on z anywhere. So if we're up here, it's pointing at 2.2. That's the magnitude and direction. Just like if we're on the top of our cube, it's also 2.2. That was supposed to be an arrow, okay? So the flux coming into the top of the cube is the same as the flux. So the flux going into the bottom is the same as the flux going out. So we don't need to worry about the electric field in the z direction either because it just sort of cancels out, okay? The one that we do need to worry about, okay, so what is the net charge contained by the cube? Well, all right, in the y direction, we are going to have to worry about it because right here we see that there is a y squared in our equation. So that means as we move in y, the electric field is changing. Okay, so that's going to be important. All right. Now, we know what the area of each side of the cube is. The area doesn't change. It tells us that our area is 2.2 times 2.2 meters. So this will be meters squared. Okay, so it's about 4.4. So the area of one side is 4.4. Wait, did I do that right? No, yeah, I think that's right. Sometimes when I'm on camera, I can't think very well. Yes, yes. Oh, you'll probably find. No, it's 4.84. Oh my gosh. All right. You know what? It's Friday and I don't care. So please don't judge me. If you had to write this on Zoom, you might, I don't. All right, so it's 4.84 meters squared. That's our area. It's the same on both sides. And now we need to find our electric field. Okay, so what is the net charge contained by the cube? All right, well, we know that we're going to have two integrals, right? So there's this integral over here, and then this back face over here. We're going to get an integral from that. Okay, so my integral is going to be E dot dA, right? And on this side, the electric field doesn't depend on how I move across that surface. So it's going to be constant. So over here, on this side, it's going to give me in the, oh, and let's back up here. Maybe I'm going to I'm going to write this on paper because then it won't be so horrible. Because if I write it on the screen, it'll be terrible. All right, so let's draw our cube. I don't want to make it any more confusing than it needs to be. And if I try and write on that little thing, it's going to be terrible. All right, so we've got our cube here. This is our cube. Okay, we've got and I'm going to draw the back face here. There's the back part of our cube. Okay, so in the back here, we're going to take into account the back side of the cube. And we're going to have to do an integral or figure out what the flux is through the front side of our cube. And the problem tells us that over here, let's see, it says that x1 equals 5.2 meters. All right, that's an important clue. Okay, so here are, oh no, it's just our y coordinate. That's all that matters. So our y coordinate, y1 is right here, and y1 is going to equal 3.7 meters. And we know that the cube is 2.2 meters long. Okay, so we're going to have one over here. So this side is going to be at 3.7 minus 2.2 meters. Okay, so 3.7 minus 2.2, that is going to be 1.5. So our coordinate over here is going to be 1.5 meters. All right, now for our electric field, okay, so we're going to have our vector here, which is E dot dA. So E dot dA, and I know that E, so I will have, it'll be 2.8 times I minus 3.6 times y squared times j hat plus 2.2 k hat times newtons per coulombs. This is going to be dotted with my normal vector. Okay, so I'm going to have this times a vector, which is going to be a times I hat plus a times j hat plus a times k hat. All right. Well, we already said that the only one that matters is y. So when we multiply this over here, none of that matters. So all of this is going to go away except these ones. So I'm going to get the integral of 3.6 times y squared and times dA. Okay. So this is constant, and so what I'm going to get is I will get 3.6 times my y coordinate, which we can do over here. So this will be my y coordinate, which is 1.5. Yes, I can move my paper up. There we go. So this is going to be 1.5 meters. Okay, so I'll have times 1.5 meters squared times my area, which is 4.84 meters squared. Right, that's going to be the flux through the backside of my cube over here. This is my flux, or we'll call that side 1. Then I need to figure out side 2. Well, I can use the same formula over here. Now I'm just going to plug in for this. So this was for side number 1. So the flux through side number 2, I'll start with my result here. It'll be 3.6 times y squared times my area, which is 4.84 meters squared. So I'll plug in for y on this side. And we said that y is 3.7 meters. So that will give me 3.6 y squared times 3.7. Oh, it's 3.7 meters times 4.84. Okay, 4.84. Now, okay, so once I get the flux from each side of this, right? So I have flux going in and flux going out. I want to get my total flux. So this is going to be flux, my net flux into the box will be sigma or psi 2 minus psi 1, right? And this will equal Q divided by epsilon naught. And someone put a comment. Oh, yes, you're welcome. All right. So now we can go over to Mathematica. And let me open Mathematica and we can plug in our numbers. So here's what we're gonna do. So for phi 1, we will have 3.6 times 1.5 times 4.84. Okay. Then for side 2, I'm going to leave that at Mathematica. I'm just going to change this number here. This is going to be 3.7. And I'll call this 2 by 2. So I'll get 64.468. Now I'm going to say phi 2 minus phi 1. And this is going to be phi total is equal to that, which is 38.3328. And I know that phi total is equal to Q divided by epsilon naught. So if I want to get Q, then I just say Q is equal to phi total. Why? So somebody asked, why don't we square the values? Did I not square oh yeah. Why don't we square those values? That's a really good question. I don't know. You are right. Probably because I'm on video, and then when I'm on video, I do stupid things, but that's okay. It's hard to think when you're doing this on on Zoom because you feel like, oh my gosh, everyone's judging me. But I know you're not judging me. It's fine. You can judge me. So the correct answer, thank you for pointing that out, Akash, is 212.399, according to my my values. All right, and then I don't know what epsilon naught is, so I'm going to ask Wolfram Alpha, and I can do that on Mathematica because it's nifty like that. Oh, so I said you have to phrase it in the form of a question. What is? Oh, did it give me the answer? No, it doesn't know. What is epsilon naught? Oh, Wolfram Alpha doesn't know how to interpret my equation. That's fine. I'm going to Google it. I don't remember. Epsilon naught value. All right. So it is 8.854 times 10 to the minus 12. Yes. So then we can multiply that and we can get our total. Yeah, so this will be times epsilon naught and yeah, epsilon naught is equal to 8.854 times 10 to the minus 12. There it is. Okay, so now we can plug this in to find the total Q value. And no, I want this value. I don't know why it's being so difficult. Okay, so I'll plug this in here. There we go. So the total Q then is going to be that. And let's check to see what the answer is. Maybe that's not right. Oh, I was close. It says that the answer is minus 1.76 times e to the minus 9. So I was really close. So I'm going to call it good enough. But that is how you do the problem. So I'm going to say that we did that one. It's close. It's really close. Yeah, I think I was. How did I mess up? Well, that's close enough for now. Did I put that into Mathematica right? Yes. Well, I think I made a slight math error somewhere. But generally, that's with the same math. Oh, wait, did I not subtract it correctly? Oh. No, I didn't get the right answer when I subtracted it, but you know what? That's fine. If Mathematica would have done the subtraction correctly, the correct answer should have been 200. And if I put 200 in times that, then let's see what it says. Yay, there we go. We got the right answer. So apparently Mathematica can't do subtraction. Oh well, I didn't know that. Let's go on. All right, let's look at another problem. That's how you do that one. That is the correct answer. Let's do another one. Oh, there's one with a net. That looks happy. Let's do this. Let's do problem 4. Or why don't I ask you? Why don't you guys pick a problem and I'll try and do it. And then we'll see what happens to old man Wisby. He'll probably mess it up, but that's okay. All right, so does somebody want to pick a problem for me to do? And we'll sure give it a try. If you don't pick, then I'll pick a problem. So is there a problem that anyone would like me to do? We can work on it together.
Number 46.
Number 46. Yes. Let's take a look. All right. I will share my screen. Nope, that wasn't it. New share. There it is. All right. Assume that a ball of charged particles has a uniformly distributed negative charge density, except for a narrow radial tunnel through its center. Okay. From the surface on one side to the surface on the opposite side. All right. Also, assume that we can position a proton anywhere along the tunnel or outside of the ball. Let Fr be the magnitude of the electrostatic force on the proton when it is located at the ball's surface at the radius r. All right. As a multiple of r, how far away from the surface is there a point where the force of magnitude is 0.58 FR? And if we move the proton away from the ball and into the tunnel, whoa, well, that looks tricky. All right, so we've got a tunnel apparently, and all right. Well, we'll sure give it a try. We'll see what happens. Maybe you guys can help me out if I get confused. All right. All right, so let's read about the shape again. Assume that the ball of charged particles has uniformly distributed negative charge density, except for a narrow radial tunnel through its center, from the surface on one side to the center of the opposite. Okay, so I guess we have, I'm gonna draw a picture here. We have a ball that somebody drilled a hole through. And our hole goes all the way through here to the other side. We got this. And now we have a proton here, and we want to know what is the electrostatic force between the proton and the ball, right? Now, how much charge does the ball have on the surface? Somebody said to do problem 35. We're going to start with 46, and then if we don't get to 35, I'll make a video about it later. All right, so, and there's going to be another video also. All right, how much charge does it have? All right, well, we know that force is equal to E time, little e, the charge of our proton, times the electric field. All right, now, what's it asking for us? All right, so what's the magnitude of the proton away from the ball and into the tunnel? If we're away from the ball, then we can just treat it as a point particle, because if we do our Gaussian surface around it, okay, it doesn't matter if it's spread out over the surface or it's all at the center or it's uniformly distributed throughout the sphere. Gauss's law doesn't care. The only thing that matters is what the total charge is on the ball. It doesn't matter how it's distributed if we are outside of the surface, okay? So then we can write that E equals Q divided by 4 pi epsilon naught R squared. R is the distance from the center of the ball over to here, okay? So the important point of the problem is literally it doesn't matter, okay? Now, for the second part, as we move into the tunnel, so as the proton goes into the tunnel, okay, now we make a new Gaussian surface, which will have a radius r, okay? And only the charge contained inside of that radius will give it a force, okay? So what's outside of the charge or what's outside of the sphere, it doesn't matter. The only thing that matters is what's inside, all right? So let's see, how can we do this? Now, let's say if we want for part A, because that was not the question. All right, how far from the surface is there a point where the force magnitude is F equal to 0.58 FR? So this is the force at the radius of the ball. Okay, so FR will equal E times Q divided by 4 pi epsilon naught R squared. This is the this is if we're at the very surface. Okay, so when we're at the very surface, if the proton were right sitting on the surface of our sphere, that would be when the charge is its strongest. As we move away, the charge is also going to drop, the force is going to drop off. As we go into the tunnel, the force will also start to decrease, okay? So then if we, all right, so how you do this problem is we know what FR is here, and we know what F is. And so we need to solve this expression. So what you're going to do is you're going to put this in here, and then you're going to substitute this in for right here. And then you're going to solve this and come up with the ratio for R. Your final answer is going to be in terms of R. Okay, so and let's see. So we can solve for R. So I guess let's try and do this. We'll get started on it and see what happens. We'll have E times Q times 4 pi epsilon naught R squared is equal to 0.58 times EQ divided by 4 pi epsilon naught R squared. All right, so we're gonna have a bunch of stuff that cancels. Oh, here, and let me share my screen for you. I apologize for making that so small. Okay, so this is just the force in general. So if we just wanted to find our force, it's somewhere outside of the ball, it would be this. This is our equation for force if we're on the surface of our sphere. We are going to need to solve this expression right here for when we are outside of the ball, right? So I substitute in for F right here. I substitute in for FR down here. And now I'm going to have a whole bunch of stuff that cancels. E times Q is going to cancel. My 4 pi epsilon naught is going to cancel on both sides. And now I'm going to end up with, I will have, let's see, I'll have R squared, 1 over R squared is equal to 0.58 times, that should be an R squared up there, divided by R squared. So now I can get this in terms of R, or little r. So it'll be R squared is equal to R squared times 1 divided by 0.58. So I'll take the square root of both sides. So R equals the square root of 1 over 0.58. Okay. All right. So that is the answer for that one. Now for the second part, you will have to figure out how to do that. Do it in a similar way to what we just did here. Okay. So, but our time is up for today. So I will post the video for number 35 later, and then I'll also give you some clues about part B for this one. So thank you for coming to class today, and have a good weekend. I hope you all do something that is socially distanced and fun. There's lots of things you could do. You could play Roblox, Fortnite. You could have a Zoom party and eat in front of each other. It's very fun to eat while you're Zooming. So it's like you get to watch your friends chew on video, just like in real life. All right, have a good weekend. Thank you. Bye.
Have a good weekend.
You
Dr.
too have a good
on
weekend. Yes,
Blackboard,
Ollie.
it says that we have to upload our test 3 work.
You can either upload it or send it to me by email. I think the link to upload it's not working right now. I'll have to fix that. But
what's test 3? I'm confused.
It should be. We've only had one test. It's test 1. So sorry.
Okay. I thought we had like a second test and a third test that I completely missed.
Whoa, I
was
must
kind
have
of
missed those two. That's kind of scary. No,
I just wanted to make sure that I wasn't
so
like.
far.
It's good.
Yeah.
And then for the partial credit, is our test total out of 13, or is it going to be worth more? If that makes sense.
Yeah. So, if you, I don't know what you got on the test, but if you missed a problem on the test and you showed your work and you sent that to me, then I can give you partial credit.
No, I mean like let me rephrase it. It's the test out of 13 points, or when you add when you add the partial credit, the total number of points it's going to increase. Do you know what I'm saying?
Yeah, I know what you're saying. So basically okay, so for the test and for your partial credit, to show your work, you need to send both of those to me to get 100% on the test. So if you did both of those, you got them all right, you sent me your document showing your work, you'll get 100% on the test. I don't know how many points that's going to end up being, but in order to get 100%, you have to do both of those things.
Okay. Thank you so much, Dr. Wispy. Have a great weekend.
You too. Thank you.
So, Dr. Wisby,
Yeah.
are the homework problems still going to be due on Monday?
The chapter 3 homework is due on Monday. Yeah.
Okay, sounds good. Thank
That's
you.
the plan. All right. Have a good weekend. Do you guys have a question?
Do you have office hours right now?
I
Or is
can.
this
Did you have a
not office
question?
hours? Okay, I don't want to like keep you.
No. If you have a question, please.
Okay.
I have time.
Did you say that you were going to do number 35 in a video?
Yes.
Okay.
We can take a look at it now if you want. I just didn't want to keep everybody because I know some people have classes and things like that. So, did you want to take a look at it right now?
That's okay. I'll just wait for the video.
Okay.
Yeah. Thank you though.
All right. Thank you. Thanks for always having your webcam on. It's nice to be able to see other people. So,
yeah.
All right. Have a good weekend.
You too.
Bye.
Thank you. Like and subscribe down below.